Hello and welcome to my presentation on cation water analysis. Cation water analysis is very important in identifying different metal ions and elements that can be found in water. This can be done via precipitation reactions where two aqueous solutions are mixed together and some of the reactants in the solution can form insoluble solid products that can be seen in the liquid solution within it. This qualitative and quantitative analysis of water for the presence of these ions is a very important tool. In group 3 cations like aluminium 3+, iron 3+, cobalt 2+, and nickel 2+, they can form insoluble sulfides or hydroxides in specific basic saturated solutions. This method is analogous to group 1 cation analysis, where a known mixture of known cations will first be prepared and analyzed as a positive control, and then an unknown sample with the one or some or all of these ions present in it can then be analyzed and compared with each other to understand the behavior and properties of these ions. When performing qualitative analysis, group 3 cations are separated from each other in order to classify the different ions present in the analyte. Then each ion has distinct characteristic tests that determines its presence within a sample. A general method for cation analysis can be where you bring in a mixture of cations in a water sample and you treat it with 6 molar hydrochloric acid and to find whether it can make insoluble chlorides, which would indicate the presence of group 1 cations. And then you would move on with the same solution and add more acid to it with 1 molar thioacetamide to see if there are any group 2 cations present. And that same solution then you can proceed with it and add 6 molar NH3 and 1 molar thioacetamide to test for group 3 cations, which would form insoluble sulfides. And for group 4 analysis, you would add 1 molar ammonium sulfate to see if any insoluble carbonate precipitate is formed. And then for group 5 cations, you can test for them via flink tests. Detailed method for group 1 analysis is shown here, where you treat your solution with 6 molar hydrochloric acid and then centrifuge it, then precipitate out the solution and add some water to it while you heat and stir. Then you centrifuge again and use your remainder centrifugate to treat it with 6 molar acetic acid and K2CrO4, which if there was any lead contained within it, it would show a yellow precipitate, but in this case there was no lead ions present. So we go back to our previous step and we use the remainder of the centrifugate and treat it with 6 molar NH3. We stir and centrifuge and you would get a grey precipitate if there was any mercury ions involved, but there were no mercury ions present. Then from that previous step, you use the centrifugate left there, and you could either treat it in an acidic HNO3 solution or crystal of potassium iodide. In the acidic condition, a white precipitate of silver ions would be formed, and in the other condition, a creamy yellow precipitate would be formed. Both of these were recorded in this experiment, and as you can see here, there's a white precipitate from the acidic condition and a creamy yellow precipitate from the other one. A detailed method for group 3 analysis is shown here, where you treat the remainder of your solution after the group 1 and 2 analysis by adding 1 milliliter of 1 molar NH4Cl, and you precipitate that out and add 24 to 30 drops more of HCl, stir, heat it, and then cool it, and then add 20 to 25 drops of water. You centrifuge it, and then you can precipitate it out and get insoluble sulfides, and then washing with small amount of hydrochloric acid and water, you could then treat the remainder of the certificate with saturated acidic solution, which would give you a cobalt ion precipitate, which we do not have in this situation because no blue precipitate was formed. Going back to the previous step, you can treat it further with acetic acid and K4FeCN6, and that would give you a white precipitate, which would show the presence of the zinc 2 plus ions, which in this case was shown in the experiment, which means we had zinc 2 plus ions in our water sample. And if you treat it with a basic pH basic solution, it could form a red precipitate if there were any nickel 2 plus ions present, but in this case there wasn't. So if we go back to our previous step and use the remainder centrifugate and add enough basic solution and then 10 more drops to stir and heat for 5 minutes, we could precipitate out an iron hydroxide solution, which in this case was observed as a brownish red precipitate in the solution, which means we had some iron 3 plus in our solution. And then if we wash it with some water and more basic conditions and centrifuge it, we could get a further form of iron from iron 3 plus ions with a red precipitate that was also observed in our experiment. And then, which means we had iron 3 plus in our solution. And if we go back to our previous step and use the remainder centrifugate and test it with more acidic and basic solutions and then centrifuge it, we could get a white precipitate if there was any aluminium 3 plus ions, but in this case there weren't any. And the same can be done to show that there are any chromium 3 plus ions involved in the solution, but in this case there weren't any as well. Detailed method for group 4 and 5 analysis is shown here, where you use the remainder of your solution from the previous tests and add 30 drops of 6 molar hydrochloric acid and enough NH3 to make it slightly basic pH. Then we can precipitate that out and wash it with water, centrifuge it, and then we could get a yellow precipitate if there are any barium 2 ions involved, but in this case there weren't any observed. And then if we use the same centrifugate from earlier and treat it with pH basic solution and centrifuge it, we could get a white precipitate if we had any calcium 2 plus ions involved, but in this case there were none present. And if we use the previous centrifugate as well and add enough NH3 to make it basic, we can get a white precipitate to show the presence of magnesium 2 plus ions, which in this case was shown from the experiment with this from this picture, and which means we had magnesium 2 plus ions in our solution. And if we use the centrifugate from the beginning, we can perform a flame test to test for various ions that could be present in there, but the flame test was only a regular yellow flame, which means none of these ions were present in our solution. And if we treat our original solution and suspend it in moist red pH paper on top of NaOH, we could test for NH4 plus ions, but in this case we did not have that. We can use the data collected from UV-Vis spectrometry of the various sample solutions with iron in them and our unknown solution to find the concentration of iron in our solution using the generated calibration curve from this data and using the equation of the line to rearrange it and find the concentration of the solution in the diluted form in 50 ml of water, and then using that value we can use C1V1 equals C2V2 and rearrange that to find our concentration of the iron in the original 2 milliliters of that sample, which would give us 1.6287 times 10 to the minus 3 molar. And using ICP method of testing for the same solution, we had a value of 91.04 milligrams per liter or parts per million for our iron 3 plus sample. So if we change that to molar by dividing first by 1,000 the value to get it to grams per liter, and then dividing that value by the atomic mass of iron, we can get a molar value for our iron 3 plus solution of 1.6302 times 10 to the minus 3 molar, which, as we can see, correlates with our value calculated from the calibration curve, which indicates the data collected are accurate and correlated between each other. A zinc 2 plus solution was also tested in the ICP method and gave us a value of 4,802 milligrams per liter and was converted in the same method to 7.3448 times 10 to the minus 2 molar. The ICP analysis run on this sample showed only 2 of the 4 present ions in this solution. The absence of silver and magnesium could have been accounted for due to the poor calibration of the machine when run with silver. As we can see, the correlation coefficient is very low compared to the other ones and a lot lower than 1. And the point values in the graph are very scattered and unaligned. For, as we can see for zinc as well, the points do not align as much and it does not start quite as on 0 as it is with iron 3 plus. For magnesium, it could have not showed up due to maybe the concentration of the precipitate form being low. As we can see from earlier, the concentration of it was not very high or as high as in different samples that showed precipitates. In conclusion, we were able to run analysis and find 4 metal ions that were identified. 2 of them did not show up in further analysis. That could have been due to poor calibration and poor handling of a new machine that was not been used properly before. Better calibration could have improved further results and shown better results for it. Thank you so much for watching.